All right, so the first piece of this is the unit circle. And again, the unit circle is formed by making a circle with a radius exactly 1 unit. And the reason this is valuable is because of our special right triangles that we've learned about before. There are two special right triangles. There's a 30, 60, 90 and a 45, 45, 90. I'm going to give you a derivation of these because I think it's super relevant to this unit. A regular triangle, by definition, means a triangle that has equal sides and equal angles. So this is the equilateral triangle. And if I were to choose an equilateral triangle with side lengths of 1, and I drop an altitude straight down, splitting this thing in half. Altitude means these two are right angles. Since they've got this side and this side is shared reflexive, these two triangles come out to be congruent. And that means that this side of 1, because they were all equilateral, has now been split into 1/2 and 1/2. And I can find the third side, x, by using the Pythagorean theorem. 1/2 squared plus x squared equals 1 squared. So 1/4 plus x squared equals 1. Subtract 1. 1 is equivalent to how many fourths? 4/4. So when I subtract 1, I get 3/4. When I take the square root, I should get plus or minus square root of 3/4. Because we're talking about the length of a distance of a triangle, a height of a leg, we don't need to worry about the negative one. So I've got the square root of 3 over the square root of 4, which simplifies to root 3 over 2. And this becomes our special right triangle. In a 30, 60, 90 triangle, the side opposite 30, when the hypotenuse is 1, is exactly 1/2, and the side opposite 60 is root 3 over 2. And again, well, we'll get to that part in a second. What's interesting is in a unit circle, we're also going to use the same triangle, but positioned a different way. This is still a 30, 60, 90 triangle. And if the hypotenuse is 1, how big is this shorter side? 1/2. Good. Remember that opposite the 30 was the shortest side, opposite the 60 is the mediumest side, and opposite the 90 is the largest side. So opposite the 30 is the shortest side, opposite the 60 is the mediumest side, opposite the 90 is the 1, the biggest side. And the same thing can be done to find the side lengths of an isosceles right triangle. It comes from a square. And if I divide a square like this, such that these sides were initially 1, this side length can be found by using Pythagorean theorem again. 1 squared plus 1 squared equals x squared. So 2 equals x squared. So x equals square root of 2. Again, we're going to ignore the negative one because it's a length. So this is one of the 45, 45, 90 triangles, but this one doesn't satisfy the unit circle value. Why? The hypotenuse is supposed to be what? 1. It's not. It's root 2 here. So how would I simplify this? How would I turn this into a 1? What could I do as a transformation, a dilation of this triangle to stretch it or shrink it down to force this hypotenuse to be exactly 1? Divide by root 2. So I'll divide this side by root 2, and this side by root 2, and this side by root 2. This becomes 1. Perfect. That's what I wanted. And this becomes 1 over root 2, which is the answer, but it's not in a rational form. We're not allowed to leave it like that. In order to rationalize it, we're going to multiply by root 2 over root 2, which gives us root 2 over a regular 2. And this is the side length ratios for an isosceles right triangle, a 45, 45, 90. When the hypotenuse is 1, these side lengths are root 2 over 2, root 2 over 2. And oftentimes people struggle with remembering these, which one goes where, right? That's the hardest part of this piece. I'd like to suggest the following: 0, 30, 45, 60, 90. Next to this, I'm going to write 0 halves. Well, square root of 0 halves, square root of 1/2. A bit this bigger so we can see it. So opposite 0, I'm going to write 0 over 2, square root. Opposite 30, I'm going to write square root of 1 over 2. Opposite 45, I'm going to write square root of 2 over 2. Opposite 60, square root of 3 over 2. Opposite 90, square root of 4 over 2. What's the square root of 0? 0. 0 divided by anything is still 0. What's the square root of 1? 1. So this becomes 1/2. Square root of root 2 over 2, that is simplified. Square root of root 3 over 2, that is simplified. What's the square root of 4? And 2 over 2 is 1. What this does for us is it allows us to fill in the x values or the y values for the coordinates around the circle. Let's take a look first at what I'm coloring as a yellow triangle. The smallest angle measure we've got is 0 degrees, right? When it comes straight across here, it's at 0 degrees. And what's the coordinate here? If the radius is 1, what's the coordinate at this endpoint? 1, 0, right? Now, I showed you this relationship, and it's going to come upon us here. This is now a 30-degree angle. And we've just talked about the fact that the hypotenuse is 1, this length is 1/2, this length is root 3 over 2 in a 30, 60, 90 triangle. Therefore, my x value is root 3 over 2. My y value is 1 over 2. Then I move up to, let's move up to this triangle. This is the same triangle. It's still the 30, 60, 90 triangle, but instead of looking at the 30-degree angle, we're looking at a 60-degree angle, which means this side is the root 3 over 2. This side is the 1/2. Hypotenuse is still 1, which means my coordinate has an x value of 1/2 and a y value of root 3 over 2. And again, remember what I said over here. If we follow this up, the y values, for example, 0, 1 over 2. This is the 45, 45, 90 triangle, so that's going to be root 2 over 2, root 3 over 2, 1. And then it works the same way going back. So if we think about the value of the endpoint when we're at the origin going straight up 1, that's 0, 1. And then as we move this way, 1 over 2, root 2 over 2, root 3 over 2, root 4 over 2, which is actually 2 over 2, which is 1. Any questions about filling in the first quadrant of the unit circle? What's your confidence? 5, I can do that all day long. 3, it's still a little rusty, a little practice, I'll be there. 1, I can't do it. Okay. Totally get that it's a little rusty. Now, when we bring these values over to here, I'd like to suggest that you think about it maybe a different way than you did in advanced algebra. I'd like you to see that, for instance, this triangle is the same triangle that we had over here. And so rather than count around this way, I'd like you to see it as what's called a reference triangle. In other words, whether I'm using this whole angle as my theta, or I'm using this little piece as my theta in this quadrant, I know that this coordinate is going to give me my sine and cosine values. So this is the point -1, 0. And how many degrees do we have going to here? Good, 180. Now this yellow triangle is a 30-degree triangle. So if I go backwards from 180 up 30 degrees, what's my degrees here? 180 minus 30 is 150. And if I go back my 45-degree triangle, 180 minus 45, I get 135. And if I go back my tall triangle, my 60-degree, I'd say 180 minus 60 is what? 120. And this triangle, just as I said, is the tall triangle. It's the 60-degree triangle. So that means it's going to have the same dimensions. The only thing that changes is because I've moved to quadrant 2 instead of quadrant 1, my x value is going to go negative. So instead of having a positive 1/2 root 3 over 2, this is going to be negative 1/2 positive root 3 over 2. And the same is going to be true with the 45 angles. Instead of it being positive root 2 over 2, root 2 over 2, it's going to have a negative x value, root 2 over 2 negative, and then a positive root 2 over 2 as the y value. And again, same with the 30-degree triangle. My wide triangle, so this is a root 3 over 2, but now it's going in the negative direction, so negative root 3 over 2, positive 1/2. And we get that same ratio, the 0, the 1 over 2, root 2 over 2, root 3 over 2, root 4 over 2. Guys with me? Okay. What's going to happen when we move down here? How do things change? It's all negative. In other words, we're going to have negative x's and negative y's. Up here, we had negative x's, but positive y's. Over here, we had positive x's, positive y's. What's going to happen over here? Positive x, negative y. Okay, would you please take a moment to fill in all the coordinates going around here, as well as the angles in degrees. Remember that we can say 30 degrees this side of 180. So what's my angle measure here? What's 180 plus 30? 210. 180 plus 45, 245. Okay, please fill this in now. All right. The last piece of building a unit circle is the what? The radians. And people struggle with this a little bit. But again, the way I've just described about adding 30 degrees or subtracting 30 degrees is going to help us with our radian measures. You're going to have to probably just memorize a couple of them. 30 degrees is pi over 6. 45 degrees is pi over 2. 60 degrees is pi over 3. What's 90 degrees? Actually, my bad. This is not pi over 2. This is pi over 4. Sorry about that. What's 90 degrees? Pi over 2. Now, if we want to come back this way, what is 180 degrees in radians? Good, 1 pi. And of course, because this is 1, this is also the same as 2 over 2, or 3 over 3, 4 over 4, 6 over 6, right? So if I want to go back up this yellow triangle, if the 30-degree equivalent is pi over 6, and I want to go 1/6 less than 1, what's my radian measure? 5 pi over 6. And since the 45 is the fourths, I want to come back up from 1/4. What if you take 1/4 away from a solid 1? 3 pi fourths. And because the 60-degree is pi over 3, we're going to be coming 1/3 back from a whole. So what's our 60-degree measure? 2 pi over 3. Now, that's not the only way to do this, but it certainly works well. I've seen a lot of people do something like, this is 1 pi sixth, this is 2 pi sixths, this is 3 pi sixths, 4 pi sixths, 5 pi sixths, 6 pi sixths, and you can count around that way. And then you do the same thing with fourths. 1/4, 2/4, 3/4, 4/4, 5/4, 6/4. That works great. Once you get more familiar with it, that might be faster, but I've also seen people struggle with which one goes where. So I think it's really helpful to visualize that it comes from these triangles. Now, what's the point of this? Well, the whole value of this is that I now know that if I want to find the sine of 45 degrees, I recognize that because this triangle has a unit hypotenuse of 1, that the sine, which is the opposite over the hypotenuse, I don't need to worry about the hypotenuse. The sine of 45 is equal to the vertical leg of the triangle made at 45-degree angle. Since I've created this, I know that the y value, which is my vertical leg, is root 2 over 2. So the sine of 45 is root 2 over 2. I can find that value precisely immediately. In general, what this tells us then is that all of these coordinates that have an x and a y value can also be thought of as the cosine of theta, comma, the sine of theta, where the x value is exactly the cosine at that angle and the y value is exactly the sine at that angle. Questions? Quick refresher on unit circle. 5. I could do the unit circle, all parts, degrees, radians, coordinates. 3. I'd struggle a little bit, but I'm getting close. 1. That's never achievable for me. Okay, good. Better scores. Your homework tonight is going to include you completing a unit circle from scratch. That's what this last page is here. You'll notice that the prior page has an answer key for you if you need to check it, but you need to get good at this because next week's test will ask you to fill in a complete unit circle. Okay? Now, we're also going to work with a couple of other things here. These are called the trigonometric identities. This is my second favorite word in all of math, trigonometric. It's almost as fun as perpendicular. Okay, the first trigonometric identities we're going to work with are the quotient identities. Why is the tangent equal to sine over cosine? How does that make sense? Any ideas? Remember the SOHCAHTOA thing? So if I'm talking about this angle, the side opposite that would be our opposite, our O. The side next to it would be our adjacent, A. And the hypotenuse, opposite the 90, would be the hypotenuse. If I take the tangent of this, what I'm saying is that the tangent of that angle is equal to the opposite over the adjacent. Now, I'm going to do a little math magic. This is a fraction, right? I can do whatever I want to one multiplying as long as I do the same to the other, top and bottom, multiply by a version of 1. I'm going to multiply this fraction by 1 over hypotenuse over 1 over hypotenuse. And that's allowed as long as my hypotenuse isn't 0, which it's not going to be for this. So that's going to be the opposite over the hypotenuse divided by the adjacent over the hypotenuse. And opposite over hypotenuse, we said, is the what? Sine. And adjacent over hypotenuse is the cosine. So this is called the quotient identity that says that the tangent of theta is equal to sine of theta over cosine of theta. And did you guys learn about cofunctions like cotangent, cosecant, secant? Okay. Every one of our three functions has a cofunction, which is basically the reciprocal. So for example, the reciprocal of sine would be 1 over sine. And 1 over sine is also called cosecant, CSC. And so therefore the sine is equal to 1 over sine. That would bring the sine back up. These 6 reciprocals, sine and cosine, sine and cosecant, cosine and secant, tangent and cotangent, you must memorize these and know the name. Why? What's the point of these? Well, we're going to want to be able to convert between information here. We're told that the secant of theta is equal to negative root 30 over 3. We want to find the cosine of that. So we look up here and we find which of these terms has both secant and cosine. What do you think? You want to use this one on the left or the one on the right? Cosine equals or secant equals? Does it matter? Really doesn't. We're looking for cosine, so I guess I'd choose this one. I'd say I know that the cosine of theta is equal to 1 over secant of theta. In this case, it would be 1 over negative root 30 over 3. How do you divide fractions like this? Keep, change, flip, copy, change, flip. So in other words, I would treat this as 1 instead of divided by multiplied and reciprocal here, negative 3 over root 30. Well, 1 times that is still just going to be negative 3 over root 30. That's the answer, but it's not in its finalized form. I need to rationalize it. How do I rationalize? Usually I think about multiplying by root 30 over root 30, because the bottom will then perfectly square, allowing the radical to go away, leaving me a regular 30. On top, I'd have a negative 3 root 30. I can factor a 3 out of the top and out of the bottom, and I'll end up with negative root 30 over 10 as my simplified value for the equivalent of cosine of theta. Easy peasy? Yeah, that'll be all right. Now, this unit, yes, you got to know unit circle. You got to know fractions. Okay? You also got to know radicals and simplifying radicals. Those three things are going to come back in full force this unit. I also want to talk, well, let's do that in a minute. Okay, flip to page 2, please. When you hear the word Pythagorean, what do you think of? A squared. Okay, so let's come back to our single SOHCAHTOA triangle. And again, so means that the sine of an angle is equal to the opposite over the adjacent. The cosine of an angle is equal, opposite over hypotenuse. Thinking too quickly. This is the adjacent over the hypotenuse, and the tangent of an angle is equal to the opposite over the adjacent. I'm going to label this OPP, adjacent, and hypotenuse. If I said the Pythagorean theorem, if I did the Pythagorean theorem here, what would I get? Opposite squared plus adjacent squared equals hypotenuse squared. Okay, that's not very much good. Now what I'm going to do is I'm going to divide everything by hypotenuse squared. I'm allowed to do that, right? As long as I do it to everything. What is hypotenuse squared over hypotenuse squared? 1. OPP divided by HYP, both of them squared, is the same thing as OPP divided by HYP, quantity squared. And this one's the same as ADJ divided by hyp squared. What is OPP over HYP? What is opposite over hypotenuse? Sine. So in other words, this is the sine of theta. When I square it, I'm going to put a squared on the end, not on the theta itself, because it's the function that's being squared, not the angle itself. What about this one? What's adjacent over hypotenuse? Cosine. Square theta equals 1. This is called the Pythagorean identity. It's fundamental to what we're going to be working with. How do we use it? Well, take a look at problem number 4 here. Find the cosine of theta and the tangent of theta if sine is equal to a negative 1/3. Okay, well, we know that we're trying to deal with sine and cosine. I see that I've got the Pythagorean identity up here. So I'm going to leave cosine as a variable. Cosine squared theta plus, instead of sine, I'll put in negative 1/3 squared equals 1. Cosine squared theta plus 1/9 equals 1. 1's the same as 9/9, so I subtract 1, I get the cosine squared of theta equals 8/9, which means the cosine of theta is equal to root 8 over root 9. How do I simplify root 8? You guys done that enough to know that? Two root 2. How do I simplify root 9? 3. So that's the cosine, 2 root 2 over 3. Is there another way to think about that? There is. We could also think about it visually. we can picture our unit circle, but not really a unit circle. It's just another graph that has been stretched as many as we need it to be, but it's still got the same angles working our way up and around here. We're saying that the sine is equal to -1/3. Remember how I said that the x and y can each be thought of as cosine and sine? So sine is the y value. If I know that the sine is a negative number, which quadrants could this possibly be in? 1, 2, 3, or 4? It's got to be 3 or 4, right? If sine is negative, it can't be up here. So I'm going to cross those out. Now, it could be either one of these, right? I could have it going this way, such that when I take the sine of this angle, I get a -1 divided by 3. Or it could be going this way, where this is my theta, and this is my -1, and this is my 3. But regardless of which one it is, if I wanted to find the cosine, all I'm looking for is this piece, and I can do Pythagorean theorem. Let's call it x. X squared plus -1 squared equals 3 squared. X squared plus 1 squared equals 9. That's really 1. So x squared equals 8. So x equals 2√2. And of course, that would be a plus or minus 2√2. And that's what's going on here. This direction shows the plus 2√2. This direction shows the negative 2√2. I just don't know which one yet. And the same answer came out here. Because when I did the square root, I really should have put plus or minus, right? When I introduce the square root, it's got to be plus or minus. How do I know if it's positive or negative? There's two answers. And so the way I figure out positive or negative is with this second piece of information they're sharing with me. They're telling me that in my situation, the cotangent of that same angle is less than 0. That's a negative number. When I think about my unit circle type grid, tell me about my x values and y values in terms of positive or negative. Positive, positive. What happens in quadrant 2? Negative, positive. Quadrant 3, negative, negative. Quadrant 4, positive, negative. Good. Now, if I'm going to take the tangent of an angle, tangent is sine over cosine, which means it would be just positive over positive in this quadrant. Would that be positive or negative? If I take a ratio of positive divided by positive, what kind of number will that be? Positive. If I take a positive divided by a negative, what kind of number will that be? Negative. If I take a negative divided by a negative, what kind of number will I get? And if I take a negative divided by positive, so this tells us that whereas this is cosine, this is sine, this is tangent, and then all those cofunctions, so cosecant would match with this one, secant would match with this one, cotangent would match with this one. These are the signs in those quadrants, positives or negatives. So if cotangent is less than 0, which of these quadrants could it be? 2 and 4. It can't be this one. It can't be this one. It's got to be one of those two. Oh, well, wait, over here, we said that it can't be either of these. Now it can't be 3. So this is my quadrant. In that quadrant, is my cosine positive or negative? It's positive. So the answer is positive. I had to do a little extra work to see that. All right. We also need tangent of theta. Tangent theta is whatever what. Flip back a page. Look at the quotient. Yeah. But we said that tangent was equal to sine over cosine, right? And we know the sine and the cosine here, right? So it's equal to sine theta over cosine theta. We know that sine is -1/3, and the cosine is 2√2 over 3. So that's the same as -1/3 times 3 over 2√2. My 3's are going to cancel. I get -1 over 2 root 2. What do I multiply by to rationalize this? Root 2, good. So I get negative root 2 over 4, because 2 times root 2 makes 4. And that's the value for the tangent of theta. New stuff, huh? Let's try another one. I'm going to have to write one for you because I don't think we have enough practice problems here. You want to find the sine of theta and the cotangent of theta, given that the cosine of theta is equal to negative 2/5, and that the tangent of theta is greater than 0. Would you please, is there a blank sheet in the back? There's a blank sheet all the way in the back. Flip to the back page, please. And find the sine of theta and the cotangent of theta, given that the cosine of theta is negative 2/5 and the tangent is greater than 0. Pause. Okay, I've seen a lot of people. You've got a lot of success with this. Let's just run through it real quick. So first thing we want to do is we want to find the sine with cosine. We see that a relationship exists between those, the Pythagorean identity that says that the sine squared theta plus cosine squared theta equals 1. In this case, we're leaving the sine squared theta. That's our variable. We're replacing cosine with negative 2/5. When I square negative 2/5, I'm going to get a positive 4/25. Oops. Equals 1. When I subtract, I get sine squared theta equals 25 minus 4 is 21/25. Sine theta is equal to square root of 21 over square root of 25, which is 5, plus or minus. I don't know which one yet. So I have to come back up and say, all right, I know that my cosine was given as negative. Cosine is my x value, and so it can't be in these quadrants because these are positive cosines. Has to be in these quadrants. I also know that tangent is greater than 0, meaning positive. Since this is a positive, when you divide that, your ratio would be positive. Tangent would be positive here. Since this is a negative positive, when you divide that, your tangent would be negative. Since this is a positive negative and you divide that, you'd get a negative. And when you divide a negative and a negative, you'll get a positive. So if I want my tangent to be positive, it's got to be either quadrant 1 or quadrant 3. I've already ruled out quadrant 1. Now I'm ruling out quadrant 2. It's got to be down here. And that's not a precise drawing by any means, but it tells me that my x is negative, which we knew, and my y has to be negative. So my solution here is going to be negative root 21 over 5 for the sine of theta. The second piece it asks for is the cotangent of theta. We can use our quotient identities for the cotangent. We know that cotangent is equal to cosine theta over sine theta. Again, that was in our first page here. And so I'm just going to substitute. Cotangent of theta is equal to negative 2 over 5 over negative root 21 over 5. Copy, change, flip. So that's the same as negative 2/5 times 5 over negative root 21. The 5s cancel, the negatives cancel. I get 2 over root 21. I need to rationalize that by multiplying by root 21. And I get 2 root 21 over 21. 21. 5. I got this. 3. Oh, so close. I'll get it next time. 1. Yeah, you did well, Mr. Erlin. Okay, pretty good. Any questions? Okay, so in your homework, you'll have just a couple of these to do. And you'll have one of these to do. We're now going to, oh, before we do that, you'll notice that I gave you the Pythagorean identity for cosine and sine, and it lists 2 more Pythagorean identities. You will be responsible for memorizing those, and because you're in honors, you're responsible for deriving the additional ones. So please watch as I do that for you. It's much easier than you think. we're saying that the cosine squared plus sine squared equals 1. We've already derived that. Cosine squared theta plus sine squared theta equals 1. Now, do you agree that I could multiply both sides by 4 if I wanted to? I could divide by 6. As long as I do it to everything, I can do it, right? So I'm going to take a chance here. I'm going to divide everything by cosine squared. I'm going to divide this by cosine squared, divide this by cosine squared, divide this by cosine squared. What is cosine squared over cosine squared? What is sine squared over cosine squared? Remember our quotient identities? Sine over cosine is tangent. So what's sine squared over cosine squared? Tangent squared. What's 1 over cosine squared? Secant squared, right? In other words, this is the same as that one. Yeah, these two are out of order, but that's okay. That's probably because it started with sine squared plus cosine squared. I'm not sure why this one reads cosine squared. If we started with cosine squared theta plus sine squared theta equals 1, and instead of dividing by cosine squared, we divide by sine squared. What's cosine squared over sine squared? Look at page 1. Cotangent squared. What's sine squared over sine squared? 1. What's 1 over secant, 1 over sine squared? Look at your reciprocals. Cosecant squared theta. And this is the other one of our Pythagorean identities. So again, you guys should be able to derive these. Questions on that process? Okay. Let's talk about the cofunction identities. If this angle is theta, then I could call this side, say, A, this side B, this side C. You with me? Just for variables. If I asked for the sine of theta, it would equal what over what? Opposite over hypotenuse, so katoa. So I'd get A over C. And if I asked for the cosine of theta, adjacent over hypotenuse, that'd be B over C. Agreed? Now, how big is this angle? Like, let's say this was 10 degrees. How big would this angle be? 80. What if this was 30 degrees? How big would this angle be? 60. What if this is 70? How big is this one? 20. So if this is theta, how big is this one? 90 minus theta. Right? Now, what if I wanted to find the sine, the cosine of 90 minus theta? Here's 90 minus theta. Cosine is adjacent over hypotenuse. And the sine of 90 minus theta. So here's my 90 minus theta. The sine would be the opposite over the hypotenuse, which would be B over C. In other words, the sine of some angle is equal to the cosine of its complement, 90 minus theta. And the cosine of an angle is equal to the sine of its complement. And that's true whether these are 90 degrees or whether we're talking about radians. And we're saying like pi over 2 instead of 90. The same relationship holds true. So that's what they're expressing here. These are all the relationships. Sine of theta is cosine of pi over 2 minus theta. Cosine, tangent, cotangent, etc. The other piece here is the even-odd identities. We've done a lot with even-odd, haven't we? What makes a function even? it's reflective over the y-axis. In other words, if we saw something like this, we'd call that even, right? What makes it odd? It's got to reflect around the origin, right? Rotate 180 degrees, look the same. The other thing we learned about is that even is where f of x is the same as f of negative x. And odd is where f of negative x is the same as negative f of x. Excuse me, that's over here. F of negative x equals negative f of x. You could multiply through by a negative and you get that f of x is the same as like a double negative for odd. So let's take a look at sine and cosine. If I were to take some angle here, and let's say that my coordinate now is x comma y. This angle is theta. Where is negative theta? It's down this way, isn't it? So how would the sine of theta compare to the sine of negative theta? Are they the same? Here's theta. The sine is this positive y value. Here's negative theta. The sine is this negative y value. So what's the relationship between these two things? Are they the same? Or do I have to put a negative in here to make them the same? In other words, sine is odd. It's an odd function. So when you put a negative in, you got to put a negative outside to balance it out. On the other hand, cosine, if I take a look at this angle, theta, and I find the cosine, which is x, right? It's this piece. Cosine of theta, and I compare it to cosine of negative theta. What if I look at this angle and also find the x? They're the same, aren't they? In other words, cosine is an even function. So that cosine of negative theta, the negative just goes away. It's the same as cosine of theta. Another way to think about this would be, I don't know, have you guys graphed sine and cosine? No, okay. Well, when we do graph them, what we're going to find is that the cosine graphs like that, which is even. But the sine is going to graph like this, which is odd. But if you don't know the graphs yet, that doesn't make as much sense. But here you can see that because I put a negative in here with the theta, I have to put a negative out front here. That makes this odd. And the cofunction will have the same relationship. But if I do the cosine of a negative, it comes out as though it never had a negative at all. So this is called even. And it turns out tangent is also odd. So how do we use this? Well, we want to be able to take this given information, sine of negative theta equals negative 0.97, and find the cosine of pi over 2 minus theta. So let's see. This screams out even odd properties. The sine of negative theta is equal to negative sine of theta. This says sine of negative theta. So I'm going to replace it with what is equivalent to it. Negative sine of theta is equal to negative 0.97. All I switched is this piece. Now, I don't like a negative out front here, so what am I going to do to get rid of it? Multiply both sides by -1, and I get that the sine of theta is equal to positive 0.97. I'm just going to sit on that for a second. What I'm aiming for is cosine of pi over 2 minus theta. Cosine of pi over 2 minus theta, that whole thing is equal to sine theta. So if cosine of pi over 2 minus theta is equal to sine theta, and sine theta is equal to positive 0.97, then cosine of pi over 2 minus theta is equal to positive 0.97. Happened too quickly? Okay. What I did is I took what they gave me and I manipulated it using these two identities to discover what this is equal to. I started by saying the sign of negative theta is given to me as this. I'm going to get the negative out of here. So I use my even odd property. The sign of negative theta is the same as negative sine of theta. So I change this to this. Now, I see a negative out here and a negative out here. That just feels sloppy. So I'm going to divide both by -1, giving me sine of theta equals positive 0.97. What I'm looking for is the cosine of pi over 2 minus theta, which we learned up here is the same as the sine. So if this thing is equal to sine of theta, and I previously found that sine of theta is positive 0.97, then I know that this thing, cosine of pi over 2 minus theta, is also equal to 0.97. Let's take a look at number 7. Yeah. You will. All right. If tangent of negative, anyone know what this is called? Alpha, good, is equal to negative 2.36. What can I change this into? It's an odd function, right? We said up here it's odd. So I can replace this with negative tangent of alpha. And I just replaced this, so I don't need to change this other side at all. Now, I don't like this negative out front. What can I do to get rid of it? Both sides. So the tangent of alpha is equal to positive 2.36. Now, we got a little work to do over here. What's wrong here? They're flipped. Do you remember me talking about this? If I have negative x minus 4 over x minus 3, do you want to leave it like that? How do we flip it? How do we change it? What makes it wrong? It's like red big balloon instead of big red balloon. It just feels wrong here. I can't have two negatives. So if I factor out a negative, I get x plus 4. But it would sure be great if I could factor a negative out of the bottom, because then I could just cancel these. If I factor a negative out of x minus 3, what do I get here? Negative x plus 3. Ooh, but that's really the same as 3 minus x, isn't it? In other words, when I factor out a negative, I just flop positions. And then those cancel. So when I see this, alpha minus pi over 2, I'm going to treat this as the cotangent of negative pi over 2 minus alpha. Because this is that cofunction I was looking for. Now, this is the cotangent of negative angle. Cotangent is an odd function. So when I have the cotangent of a negative angle, it's the same as negative the cotangent of the angle. So I can rewrite this as negative cotangent of pi over 2 minus alpha. Well, what's the relationship between tangent and cotangent of pi over 2 minus alpha? Tangent is equal to cotangent of pi over 2 minus alpha. So if I take this part, forget about the negative for a second, and replace it with tangent of alpha, because of our cofunction identities, this piece is equivalent to negative tan of theta, tan of alpha. We said here that negative tan of alpha is negative 2.36. So this is equal to negative 2.36. I know some of you would like more practice on this. So I've prepped an additional sheet that has like 3 or 4 of each of these, along with the answer key. It's posted on Canvas as an optional assignment. You don't have to do it, but if you want a little more practice playing with it, you may do that. That's the end of today's instruction. Your homework tonight is to both complete a complete unit circle and finish the little problems in here. And I would suggest you begin memorizing the cofunction, even, odd identities, trigonometric identities that are basic.